Okay, the light's gone green, so let me welcome you all to this afternoon's seminar. It's a great pleasure to introduce our speaker, Scott Harper from the University of Bristol. He's speaking on 3/2 generation.
Great, thank you Tim, and thank you for the chance to be at the I&I this month. It's been really lovely. So yeah, I want to talk about a topic in group generation, all kind of on this theme of a definition I'll give later, 3/2 generation. And this all begins with a theorem that many of you will be very familiar with. The theorem is that any finite simple group is 2 generated. So this is a theorem which relies on the classification in multiple ways. But in the most obvious way, that the way you prove it is by going through it. So the cyclic groups, which will never be mentioned in the rest of the talk, also the groups are non-cyclic from now on, are obviously 1 generated, and hence 2 generated. The alternating groups are 2 generated. It's an exercise we give to undergraduates. The sporadic groups are 2 generated, and this can be done computationally. And then the groups of Lie type remain. So I'm going to attribute this in a kind of slightly chronological way to Steinberg in 1962, who proved this for the groups of Lie type. And he did it in a very concrete way. So for each family of finite simple groups of Lie type, he gives a pair of generators. It's very concrete. And he mentions at the start of this paper, perhaps a stronger thing is true. Perhaps you can, he says a few things. And the strongest thing he says is, perhaps it's the case that if you give me any non-identity element in the group, something else generates with it. So every non-trivial element can be extended to a generating pair, like a 2-dimensional vector space. Yeah, he leaves that open. And he says, if you were to prove this, it would require techniques very different from what's in this paper. And 40 years later, it was proved. So let me give that a name. In fact, this name, and I'll state a theorem. So a group G is 3/2 generated. I'm not quite sure who's responsible for this piece of terminology. G is 3/2 generated. It's not me. If for all non-identity elements of the group, there is another element. So for each one, there is something depending on X, that generates with it. So that's the idea that kind of Steinberg said maybe this is true for finite simple groups, and the theorem makes the difference. So this is a result of Guralnick and Kantor in 2000. G, any finite simple group. Is 3/2 generated. So, what should I say? So they actually proved something stronger than that. And I'll mention the stronger thing they proved later. But for the time, let's just say that that's what they proved. So I guess the main question I'd like to kind of talk about in this talk is, well, the finite simple groups are 3/2 generated. Are they the only 3/2 generated groups, right? How strong is this property? Is this a property that lots of 2 generated groups have? Is this a property that very few 2 generated groups have? So that's the main question, I guess. But before I kind of get onto that, I'd like to give maybe several examples just to see 3/2 generation in action. Examples. So let me begin with the example, a finite simple group, the monster. So if I take the monster, and I take an element in the monster with order 59, and 59 is one of the largest divisors, and the second largest divisor, of prime divisor, sorry, of the, of the order of monster. The largest divisor is quite large. It's the second largest prime divisor of the order. And I look at elements of the order. There's a unique maximal subgroup containing such an element. That's a fact. statement of fact. There is a unique maximal subgroup H of G such that S is contained in H. For its worth, H is PSL to 59. Now, so you can, I'm not going to justify this really, but this is the only conjugacy class of subgroups that have elements of order 59, and then there's a kind of reasonably straightforward argument, there's one conjugacy class of them, and there's one conjugate in that class. But there's a unique on-the-nose subgroup containing, maximum subgroup containing S. Okay, so now if I take the intersection of all of the G conjugates of H, the normal core, that's obviously a normal subgroup of G, and G is a symbol, so it's the identity, so as a code-free subgroup. So what's that saying? Well, that's saying that if I take any non-identity element of the group, X, then it has to miss one of these conjugates. Because if it was in them all, then it'd be in the intersection, which is trivial. So for all non-identity elements of the group, there must be some G in G such that X is not in that conjugate of H. Not in, thank you. Not in. And now I claim that this kind of bit here is exactly the same as saying that X generates with, it certainly implies that X generates with S to the G. Because, let's think, X, well this is a group, it's a gent group. Now, X and S to the G generate something, evidently. They generate a subgroup. That subgroup will be contained in a maximal subgroup. And, well, what could the maximal subgroup be? Well, the only thing, proper one it could be is S to the G. Sorry, H to the G. That's the one maximal subgroup that contains S to the G. But it's definitely not H to the G because X is not in there. So this is the whole group. So what am I saying? I'm saying that I've proved for all non-identity elements in the monster, there is something in this conjugacy class, S to the G, such that X and Y is G. So I've actually proved a much stronger thing than 3/2 generation. I've said that if you give me any non-identity element, all I had to do was say there's something that generates with it. What I've actually done is I've said there's something in this conjugacy class that generates with it. So just from your future reference, I'll just quantify at the start here, and I'll give this a name, a star, property star. So for what it's worth, if you've heard anything on this topic before, this is the kind of uniform spread one property. It doesn't really have a catchier name than that. But I was going to call it property star for the point of this talk. Okay, so that's something we proved that the monster, assuming something quite strong, it proved that the monster is 3/2 generated, in fact has the stronger property. We can do better, right? Because this was overkill. This is a really quite small subgroup. You don't need to take all the conjugates to get the identity. Right, in fact, I can find, you'll need two. There's an element in the group such that H intersect H to G is true. So I'm not going to prove that, I'm just going to rephrase it. So this is exactly to say that the least number of G's you would have needed to intersect to get the identity here is exactly the base size of the action of G on the cosets of this subgroup. So let me just say that. So that's the same as saying that the base size of G acting on these cosets is 2. So I'm never going to talk about bases again in this talk, so I'm not going to give the definition. But for people who don't know, I guess, for groups acting on a set, there's an important idea, a subset of the set you're acting on called a base. They play an important role in computational group theory. They've been studied theoretically since kind of the early stage of group theory. They've been the subject of important conjecture recently, Pieper's conjecture, the Cantor conjecture, and therefore, in particular, for almost simple groups acting primitively, which is what we've got here, we know lots of things. And particularly, we know that most such actions of the monster have base size 2, including this one. So how does that translate into generation, using this connection with base sizes? That tells us that something even stronger than this, right? For all non-identity elements of the group, that, how would I say it? X either generates with S, or X generates with S to the G for this G. Right, earlier, by the same argument as up here, I don't need to take all the conjugates of S, I don't have to take all the conjugates of H, I only take 2 conjugates of H, I only have to take 2 conjugates of S. Great, that's actually really quite a strong property, right? I'm saying I can find 2 elements, they have order 59, they're conjugate, and anything in the monster generates the entire group with one of those 2. And in fact, actually, if you randomly choose 2 elements of order 59, it'll probably work. And it probably generates both. It's a really strong version of that statement. Okay, so I've talked about one group. So let me just put this into a bit of context. It's a good group, I think. So this statement here is the stronger version of 3F generation that I said that Guralnick and Kantor proved. So this statement here is true for any finite simple group. You can always find a conjugacy class that can exhibit this 3F generation property. This here is not true for every finite simple group. But let me just say it. Lots of finite simple groups have this property, and there's a near classification of such groups. In general, you can't even find a constant number that works. In lots of known, I'm just going to say it's got a title. This topic is called uniform domination. And it's something that Tim and I have thought about in the last few years. For other finite simple groups in general, results related to that, but not exactly that result. Okay, that's one example, a finite simple group. Now let's try to drop some of those adjectives. So let's first begin by dropping the word simple. Can we find another finite group that is 3/2 generated? So let me do that now. I've already forgotten my master plan for doing these boards. Okay, I'll start here. Let's consider the symmetric group where n is at least 5. So they're not simple, but they're not far from being simple, and they are 3/2 generated. So this is this result and the result for alternating groups has been known for over about 80 years. A result Picard in 1939. Okay, G has star. Right, so you can actually always get this stronger uniform spread 1 property. Well, that's actually false unless n is 6. So symmetric group S6 is the weirdest symmetric group. It's the only symmetric group that is not its own automorphism group. And somehow all those facts are related to the fact that this is a counterexample. I'll just maybe say a tiny bit more about that. If I replace this G here with aut G, the automorphism group of G, then this now becomes true for S6. Somehow if I don't have to I don't have to find a conjugacy class that works, but I find an aut G class that works, then that fixes it. But somehow that's lots of groups are not their own automorphism group, and you don't have to make that correction for any of the other ones. So I don't think that's an excuse. It genuinely is just a weird exception. This is the only known finite group, only known group, which is 3/2 generated but doesn't have this stronger uniform spread star property. Whenever you can find an element that generates, whenever for an element you can find something that generates with it, that can always be assumed to come from a fixed class, apart from S6. Anyway, fine, that's an example. Third and final example. So in the game of removing adjectives, let's now remove the word finite. Can we think of some infinite groups that are 3/2 generated. We've been through this rigmarole before with Colvin Adams, so they're banned from this game. Can anyone give me an example of an infinite 3/2 generated group? Great, that's usually the second answer, but yes, thank you, if it's ever given at all. Great, Tarski monster. So, what am I saying? 3/2 generated infinite groups. So, leave a space. Tarski monsters. So, Tarski monsters are these. Tarski monsters are these infinite groups, which have the property that for a fixed prime, every proper subgroup is a cyclical group prime order. So they're infinite, but all the subgroups are tiny. So from the definition, you can immediately deduce that they're simple, they're 3/2 generated. You can't immediately deduce that they exist, but they do. So you can see they do exist. So there's a P in the definition, right, for P at least 10 to the 75. That's a result of Olshansky from 1980. That's maybe been improved since then. Okay, any other examples of an infinite 3/2 generated group?
Infinite cyclic group.
Infinite cyclic group, great. Okay, so this example is boring, but thanks for giving it. It's an example. This example is terrifying, but yeah, thanks for giving it. And as far as I'm aware, there are no other known examples. Except, so based on the fact that there are no other known ones, Casey Donovan and I tried to see if we could find some, and we did. Is this going to go wrong? Do you want to write all this? Okay, great. Theorem, actually, before I state the theorem, I'll tell you the group. No, I'll do the theorem first. Theorem. Thompson's group V is 3/2. So that's a theorem of Casey Donovan and me last year. So what is Thompson's group V? Thompson's group V was the first known example of an infinite, finitely presented simple group. So an infinite simple group that's finitely presented. Discovered by Thompson, Richard Thompson, in the 60s, and until 2000 was apart V and its relatives until 2000 were the only known examples of such groups. Berger and Moses gave other examples in 2000. So why might a finite group theorist think that such a thing is 3/2 generated? Well, the intuition is, well, V acts by homeomorphisms on Cantor space, but it does so in a quite combinatorial way, and it does so in a way that's somewhat analogous to how Sn acts in its natural way on n-points. So for example, Sn is generated by the set of transpositions, and there's a set of involutions in V that somehow in Cantor space pick up two basic open sets and swap them. So they're like transpositions. So that kind of parallel holds enough that you can prove this. Okay, so I've given lots of examples of 3/2 generated groups. Some are finite simple, some fail to be infinite, some fail to be finite, some fail to be simple. Now, if you look at the non-simple ones, they're not far from being simple. Right? This has an index 2 simple subgroup. And it turns out that sort of thing always has to happen. So proposition, if G is 3/2 generated, then every proper quotient of G is cyclic. Every proper quotient G is cyclic. Right, so a simple group is a group for which every proper quotient is trivial. Right, so this is somehow related. Every proper quotient is cyclic. And this is easy to prove, so actually let me just prove it. So assume G is 3 halves generated. Let N be a non-trivial normal subgroup of G. G is a 3 halves generated group, a non-trivial normal subgroup. I want to show the quotient by that is cyclic. So let small n be an element of big N, non-trivial. Then G is 3 halves generated, so it's contained in a generating pair. So then there exists X in G, such that X and N generate G. And now I go to the quotient, you can see it's cyclic. So G, X, N, and NN generate G by N, and this is just X to the end of the quotient. It's cyclic. So the class of 3 half generated groups is restrictive. You have to have this property that every proper quotient is cyclic. So you're not terribly far from simple, but still quite far. So this will include, for example, every almost simple group that's a cyclic extension of the simple. Okay, great. So you can ask the question, is the converse true? Okay, it's false for a whole host of reasons if you allow your group to be infinite. So the rest of the top groups are finite. If you restrict yourself to finite groups, however, the conjecture is this is an infinite length. So conjecture with Breuer, Guralnick, Kantor from 2008 is that G is a finite group, and G is 3 halves generated if and only if every proper quotient is cyclic. So, if you were to prove this conjecture, or in proving this conjecture, an important case would be to prove it for the almost simple groups. The non-simple ones, the ones that have cyclic quotients. Prove it in the almost simple case. So, let's think about how you might do that. How would you prove this for almost simple groups? So let's think. If the socle is a sporadic group, then again it's a computation. Some of these computations aren't trivial, but it's a separate case. That if the socle is alternating, then essentially you're AN or SN, and we've seen those are 3 half generated. So you're a group of Lie type. So if you are the socle of PSL, then Tim and Simon Guest proved that these groups are 3 half generated. And in my thesis, I proved it for all almost simple groups. So let me state that. This isn't preprint yet. So the conjecture, let's just say, conjecture, which I've covered, is true if G is almost simple. Now, so I'm conscious that I've just added in the word almost to a theorem we knew 20 years ago. So I guess a lot of the next 20 minutes should be me trying to convince you that that's a non-trivial word. Some funny things can happen in almost simple groups. So let me just, I'm not going to tell you how this proof goes, I just want to tell you about one ingredient in the proof that I think is really quite useful. So for some context, let's just set up the general strategy for proving this first. So let's think strategy. So one, we're going to prove star.
Do you mean so your view of almost simple group needs to have a cyclic quotient? That's right? So
That's right.
It's
So,
not any almost simple.
Yeah, exactly. I'm saying the conjecture is true for almost simple groups. So you're right. Another way of saying it is that almost simple groups for which every proper quotient is cyclic.
Oh, okay, right. Sorry, I understand.
Generated.
Sorry, I was confused.
No, that's good to point out. I'm definitely not saying that all almost simple groups are 3 half generated. There is some are non-cyclic quotients. Okay, so the strategy for proving this. So I'm going to prove star. So this continues the idea that any group with 3 halves generated actually should have this stronger property. I'm going to prove star. So I need to do this bit first. I need to identify a class to work with. So I haven't rubbed it off yet. So the monster. So what do we do here? We found an element with a reasonably large and restrictive order. And we did that because we wanted to restrict the maximal subgroups that it could be contained in. Because the idea is that somehow if you're only contained in few and small maximal subgroups, then you generate with lots of things. So that should be the general strategy. So we're going to have to notation. So G is an almost simple group with cyclic quotients. This is simple, and this is in the automorphism group. And I'm going to have to find some element S in G with some properties. Okay, so first observation. Without loss of generality, S is in that coset. Let's think. S is definitely not in the simple group, right? Because remember, everything has to generate with some conjugate of S. Every conjugate of S is in T. So elements of T are not going to generate with it. So you're going to have to be outside the simple group. And for the same reason, you're actually going to have to, the quotient's going to have to generate, you're going to have to generate the cyclic quotient. So you're in that coset without loss of generality. Okay. And then I want a vague thing. I want to be in few and small maximal subgroups. Right? So S is in few, and then when in some small maximal subgroups. Once you've kind of done that, I'm going to say nothing really. You apply a probabilistic method. It involves studying these maximal subgroups. It involves these quantities known as fixed point ratios, and it's this part here is the method kind of, I guess, instigated by Guralnick and Kantor, but they did it for the simple groups. Now, the fact that it's a probabilistic method is interesting because this is in contrast with Steinberg. Steinberg, when he proved the groups were 2 generated, gave you 2 generators. Here, we're giving you the class, but we're not giving you the conjugate. We're just saying you can find one and maybe you can find with high probability. Okay. So I guess I want to talk about, how do you find this element? Because it has to be, you're in a coset of an almost simple group, and that's sort of an uncomfortable place to be, because you want to be in the simple group. So how do you get around it? Okay. So let's just make up a diversion. So the example I'm going to work with is kind of groups of so-called PSL NQ. And I said actually this is the one example I should be talking about, because this was work of Tim and Simon Guest. But kind of if you go to other classical groups, they're kind of a can of worms that you have to open and well, yeah. It's a nice can of worms, but it's a can of worms nonetheless. So example. Okay, I'm always going to work with SLN because it's easier. This should really be PSL, but for the purpose of this talk, you're SL. So T is SLNQ, and I'm going to let G, maybe before I do that, this naturally lives as acting on this vector space, and it'll be useful for me to write this vector space to the basis. 1 up to Dn, and I'll write Q's prime power, something like that. Okay, so that's a simple group essentially, and an almost simple group. So I'm now going to give you an automorphism, and the automorphism I'm going to give, I'm going to describe how it acts on the vector space. And it's just the standard field automorphism. So that takes some vector in the vector space and raises this scalars to the power p. So the group that these generate in called G is the group of all kind of determinant 1 linear maps and these semi-linear maps. Some people call this sigma Ln. Determinant 1 semi-linear maps on a vector space. Linear maps and then this field automorphism. Okay, and my point is that if you act similarly in a vector space, it's harder to get a grip on what's going on. So I want to ask two questions that I guess I really don't want the answers now. I would be interested in people's general impression of these questions. So what are the G conjugacy classes in the coset TG? Remind you, that's SLNQ. I don't necessarily want to tell me exactly what they are or how many there are, but like if I asked you what are the conjugacy classes in SLNQ, you'd probably say to me, oh, you can work it out based on eigenvalues and Jordan forms, right? What's an answer of that level of vagueness for that coset?
Shintani descent.
Yeah.
Pardon?
Shintani descent.
Right, good. That's exactly what's coming next. I'd like to know, can you do it without Shintani descent? Is that working? Is there an obvious way of doing this? Okay. Similar question, to which the correct answer is Shintani descent. How do elements of this coset act on the vector space? Let me ask something more precisely. How many case spaces of U are fixed by an element in the coset? Right. So again, if I asked you about SLNQ, you tell me you work out the fixed subspaces by looking at eigenvalues and Jordan forms, right? So again, what's the analogous answer for these semi-linear maps? Is there kind of an easy geometric way of seeing it? But, as you said, there's a really nice way of seeing it. And it's called Shintani descent. Great. So remember, the whole reason I've introduced this is I was wanting to identify a nice element in that coset to do all the generation stuff. So this is the way that you can do it. So the context is quite general, so I'll state the general context to make the point, then I'll give you this example. So the general context is you take a connected algebraic group. Algebraic group to me always means linear algebraic group over the algebraic closure of a finite field, say. So the example here is SLN FP bar. Now I want to take a Steinberg endomorphism of X. So the example here with a bit of abusive notation is the automorphism of X that takes a matrix and raises each entry to the p power. It's an automorphism of the group. And a bit of notation, so that's the general context. A bit of notation, X sigma will be all the things in X fixed by sigma. And so in here, that's just SLN E. Right, so that's the general setup. And you can see these are exactly the objects that we wanted to have in play. Maybe recall Q was P to the F in our setup. So if I look at fixed points under a different map, I get SLN. So I've done nothing terribly surprising so far. The way to think about finite groups of Lie type as fixed points of algebraic groups. Okay, now here's Shintani descent, which can go there, I guess. So let's say this is due to Shintani in some year 77? 76. Okay, and actually work of Kawanaka a year later. but let's push it down. So there's a bijection. The content of this theorem is that there's a bijection. So there's a bijection from where to where. So it goes from x sigma to the f classes, I'll parcel this in a minute, of x sigma to the f, this coset, x sigma classes of x sigma. Right, so in our example, ignoring the fact that it's a map on conjugacy classes, in our example, that's with the map. Right, so there's a bijection between the number of conjugacy, SLNQ conjugacy classes in this coset and SLNP classes in this subgroup. Particularly these two sets are the same size, same number of conjugacy classes. And I can tell you a little bit about the bijection, so I may as well do. Indeed, f of some g sigma, essentially all you do is raise it to the power f. But then you have to conjugate by some element of the algebraic group that depends on the g. But up to conjugating the algebraic group, this is what you're doing. You're essentially just raising it to the power f. And you can see this, that taking the sigma to the f disappears the sigma, right? So it's not a mental thing to say. Okay, so that's nice. There's a bijection. So does that answer any of our questions so far? Well, it tells us the number of conjugacy classes in here. It's the same as the number of conjugacy classes here, which you can determine by standard linear algebra means. Okay, but it actually is more than that. Because if you have a map between two things, you'd hope that the map preserves some sort of structure. This is obviously not a homomorphism or anything. So you can ask, can you preserve any nice properties? So maybe just tell you in our example where x is SLN and sigma is the normal raising to power p, here's the fact. The number of k-spaces for some fixed k fixed by g sigma, so kind of the semilinear map acts on the vector space, not linearly, but it acts, and it preserves subspaces. So the number of k-spaces fixed by g sigma equals the number of k-spaces, so I guess of fq to the n, equals the number of k-spaces of fp to the n fixed by f. So some information transfers. So again, that answers this question here. So the point is, we can now get our hands on elements in this coset, which at one point sounded terrifying. Because what you do is you say, I want to pick an element in that coset to do some generation problem. So I pick an element I like over here, and I know there's something that maps onto it. So I'll work with that element. It lies in the right coset, and I know it can preserve some nice properties like k-spaces. So let me just say that. So return to the problem. To generation, choose S by so I'm hiding lots of details. This is a very nice case in SLM, field of morphisms. The theory is much more complicated in general. I'm also hiding, what would I want to do with this? I want to find the maximal subgroups that it's contained in. So this helps me think about reducible parabolic maximal subgroups. But there are lots of other types of maximal subgroup, and such information doesn't easily transfer over necessarily. So that's that. Let me just maybe finish then just with one example that shows where things can go wrong. right? Because this is misleading. This shows that everything just is lovely, which it is in this case. So. Okay, so we're in a different classical group now. So I have my group being SPNQ, so the finite symplectic group, and I'm going to assume that Q is even. So that it gets almost simple. It's a simple classical group, so I'm going to have to study it to prove that theorem. And let's think about some subgroups that might be contained. Okay, no, sorry, sigma is the same as before. Squares and matrix entries. So SPNQ in even characteristic has a really big subgroup that's not just one of stabilizing subspaces, it's an orthogonal group. So let's go H, S, sorry, O, N, H plus is plus Q, and H minus is O minus N. These are two subgroups that both live in the symplectic group. If you preserve an even characteristic, you preserve a quadratic form, then you also preserve a symplectic form. So you get this containment. Now, I'd want to know if I took, and maybe actually I want this one, I want to think of these as subgroups of a G. I'm giving you the G. Bad board management. So, T symplectic group, I've got an automorphism. I'm wanting to consider the almost simple group, and I get two subgroups. These live in the simple group. They somehow extend to bigger groups in the almost simple group in some way. Okay, so I want to know, I have a Shintani map, SPNQ, sigma, to SPN2. That's exactly the same as what we had before. SLN to SLN, and we've got SPN to SPN. The P is this P prime is a 2 in this case. On conjugacy classes. So if I picked an element over here, and so f of g sigma equals x. Yeah, that's right, f of g sigma x. So g sigma over here goes to x over here. If I know which or how many orthogonal subgroups over here I live in, can I predict how many orthogonal subgroups over here I live in? Because we can do it with parabolic subgroups. That'd be the next step. Can you pass information across like this? And it turns out you sort of can, but you can't quite. And I'm just going to present the example. I'm not going to fully explain it. I just want to show you the sort of weird thing that can happen. So let me also take over here the K plus is a choice of O and T plus K minus T. And it turns out that the number of conjugates of H plus the number of conjugates of H minus containing G sigma on this side equals the number of conjugates of K plus the number of conjugates of K minus containing G sigma. What's not true is the number of plus type orthogonal groups that contain this equals the number of plus type orthogonal groups that contain this, and minus and minus. It doesn't split like that, but the total number does equal the total number. And this is somehow to do with the fact that when I set up Shintani descent, I insisted my algebraic group was connected, and people who work with algebraic groups will know this is not connected. As index 2, there are two types. I have to add up the two types. All those big pieces of information are probably related in ways I don't quite understand, but that sort of thing can happen. So an example within the example, just so you're a bit lost, you can follow. So an element over here, I could just take sigma itself. That's an element in that coset, right? f of sigma, I told you that sigma, this map is essentially raising to the power f. So this goes to the identity. Right. So let's maybe assume that f is just 2 to begin with. Now, over here, clearly this is contained in every conjugate of this, and every conjugate of this is the identity. So there are how many conjugates? There are 2 to the n over 2 minus 1, 2 to the n over 2 plus 1, I think. You can be going around. 2 to the n over 2 minus 1, 2 to the n over 2 plus 1. I think that's the number. That's the total number of conjugates of that subgroup. And if you add them up, you get what? 2 to the n over 2 to the n, I think. I think that's right. Okay, and that works. It turns out this sigma is contained in that many conjugates of these added together, but actually they're all that type. Because this, another fact, there are no elements of order 2 in this coset for minus type orthogonal groups by some theory. So you can really see here, they're essentially evenly split on this side, but they all come to 1 on that side. So it is in general false. To add to the mystery slightly more, when we explain it, here, they're all contained in the plus type. On this side, they're all contained in the suckle, the omega. So somehow, and actually in general, if f is even, that's what happens. The omegas over here correspond to the plus types over here, and the non-trivial coset over here corresponds to the minus type over here. But it seems like that's only true when f is even. And fine. Anyway, I think so. What was the point of all of this meandering about Shintani descent? I wanted to come up with discuss how you pick elements in almost simple groups in order to prove they have this strong uniform spread property, the strong 3/2 generation property. And the way you get your hands on elements in this coset is to invoke this theory from algebraic groups, Shintani descent, and you can see that you can, by picking elements in a matrix group that you understand, you can transfer that over to a coset you didn't understand, and some information transfers over with it, like number of k-spaces fixed if you're in SL, but some things don't neatly transfer over, like some other big subgroups. These are orthogonal groups. And this was all to prove that almost simple classical groups are 3/2 generated in a wider program to classify all the finite 3/2 generated groups. And I'll stop there.
Okay, thank you, Scott. Any questions?
Oh, I got a comment and a question. So the comment is that Deschandet has a nice definition of Shintani descent for disconnected groups. And this definition will mix the rational forms. So probably you could explain what you observed in this case. And when just for order 2, if the group of components is of order 2, it should be quite workable. So I will give you the pointer. And now a question. So
yes.
It's already not very easy for the Frobenius, but if you have a more complicated automorphism, which is a product of Frobenius by diagonal, by diagram, can you manage easily? Or
yeah, exactly. So maybe not easily. So you're right. You have to line things up properly. If you have you're right. If you had say a graph automorphism here, you might end up getting a unitary group on one side instead of a linear group, because the graph automorphism will twist when you take fixed points. So depending on the parity of f. So sometimes you might want to get a unitary group, because that's a group you have to consider. But sometimes you might not want that, and you might still want the graph automorphism, in which case there is a way of doing it, but it's not an out-the-box application of this theorem. You have to...
And the diagonal automorphism?
Diagonal automorphisms don't... so diagonals alone don't cause problems. Diagonals times graph do. Somehow the diagonals, when you take fixed points here, you get the simple group and the diagonals. So if you were doing this with, that's why I didn't do PSL. If I did PSL as my algebraic group, I get PGL here. But you can then split off the simple and diagonal. There's a way of doing that. So they cause problems, but ones that you can attack.
Do you get like an issue with somehow with the Frobenius, when you look in the coset, there's only going to be one conjugacy class in the coset, right? Whereas for a graph, there could be multiple
Yes.
multiple conjugacy
That's
classes.
right.
So does that cause issues?
Yes.
Okay. That's usually hard. So what do you actually do? You're not using Shintani descent for a graph automorphism.
Oh, just for a graph, you mean like no, you don't. No.
So
If you have a
some-
graph times a
So you have some different methods for doing.
Yeah.
Because even in the coset of the graph, right, there could be graph times diag.
right, yes,
There could
exactly.
be something different, right,
That's
as
right.
well. In the,
So an example of that is you're in just an orthogonal group and you want to look at like reflections. Yeah, so there are kind of, and those cause big problems because actually these elements fix lots of points in a vector space, so they are really bad at generating. So yeah, so graphs do cause problems.
Okay. Any other questions? What about infinite groups then? So you mentioned Thompson's
Right,
group V.
Yep.
What about other
other ones.
infinite groups? Thompson's
So-
other groups?
So yeah, so I stated it just for Thompson's group V. Actually, we proved for two infinite families of groups that are the generalized Thompson's group. So one of those families is just called MV, and it acts on a product of Cantor spaces, product space. There's also one called Vn that acts on, so Cantor spaces 0, 1 is product. So if I take that up to n minus 1, I get something called Vn. Now, I said earlier that Vn is a bit like Sn, but I also said that Vn is simple. And there's a tension there, right, because Sn is not simple. So in general, Vn, if n is even, this is simple. And if n is odd, then the derived subgroup is simple and is indexed to in the index. So this is something like an and something like Sn. So these are all 3F generated. These ones are simple, these ones are not. So we do get examples of lots of infinitely many infinite groups that are 3Fs generated. Some are simple, some are not simple. Other than the two I listed and all these Thompson ones, I don't know any examples. The conjecture that a group is 3F generated only if every proper quotient is cyclic is false for infinite groups. I know no counterexamples for two generated groups. So I don't know any examples of a two generated infinite or finite group for which every proper quotient is cyclic that isn't 3Fs generated. But also I just don't know any examples. Right, so,
So how false is it for infinite groups?
Well, okay, so
if you look at just infinite groups, for instance.
yeah, okay, so I guess it's false for silly reasons, right? So there are simple, let's just say simple groups, because simple groups satisfy the hypothesis of every proper quotient being cyclic. You can have non-finitely generated simple groups, so A in infinity. Even if you insist that they're finitely generated, there exist finitely generated simple groups that are not two generated. There's a question in the Krovka notebook that was answered by Guba in the 60s, I think. So then you're kind of down to two generated groups, and as I say, I don't know any counterexamples there. Does that kind of answer? But as I say, I just don't know many examples of, say, two generated simple groups.
Okay, so if there are no further questions, let's thank Scott again for his talk.